brings back like PTSD, that click down, because then now I'm recording. Most of your teachers use Screencastify if you watch their terrible teaching videos from online teaching. Okay. Hello at home. How's it going? Oh, this is biology. I'm wasting precious time. Okay. So head back 2 or 3 and you'll see this, that we didn't do this slide. It's got a graph on it. So find Deadpool, go back 2 or 3, and we're going to be graphing a pressure system. So we've never done this before. We did talk lots last week about how pressure affects the system, and it's kind of hard to wrap your head around. This system says if volume is decreased, what will happen? And we didn't do this, did we? I swear we didn't do this. No. Okay. So if we decrease volume, what happens to pressure? Does pressure go up or down? Up. It's inverse. Okay. Now, pressure and Le Chatelet's principle only affects gaseous systems. So is this a gaseous system? Then you add up the actual molecules or moles of gas on either side to compare. We have 2 molecules of SO2, 1 molecule of O2, and 2 molecules of SO2. So add this up, it's 3 versus 2. Those are the molecules in the system. If you increase pressure, everything gets closer together because the volume's gone down. Just like if the walls of this classroom started to shrink on us, the probability of us bonking into each other would go up. If the probability of us bonking into each other goes up, the chances of this side bonking into each other to form this side increases. So that's the theory. The other thing was we wrote shortcuts, if you remember last week. As you crush a system, it will always shift to where the least moles of gas are. So the system is forced, in this case, right. Okay, so we did talk about that last week. I know last week was like a lifetime ago because we had a 3-day weekend. What the heck does that look like when you graph? Very different. When you graph a gaseous system, the graph goes bonkers, crazy go nuts. So SO3, O2, SO2 are trucking along at equilibrium, la-di-da, life is good. At A, volume is decreased. Now, the first thing that happens at A, if you decrease the volume, is that everything goes up. Everything spikes on the line. Why does everything go up? We didn't say everything goes up. We said it's going to shift to the right. The reason why everything goes down is that this side is measured in concentration. If you remember, if you decrease volume, the concentration of everything goes up because you have less space for it to take part in. Concentration is chemical amount per volume, chemical amount per space. The easiest way to show this is mathematically. So if SO2 before the crunch was 1 mole per liter, let's just say it was 1 mole per liter, okay? And we cut the volume in half, it would spike to 2 moles per liter because 1 mole in 1 liter is 1 mole per liter. But if the volume gets smaller, maybe it's 1 mole in half a liter. So the concentration goes up. That is mathematically why when you crush a system, the concentration of everything goes up. It's annoying, that's the theory. So you can either memorize the theory or memorize that as volume goes down, concentration goes up. This little thing right here, this little shortcut. So that's what happens. Now, everything spikes on the line. This is good on a diploma because if you see a question and it's like, hey, nerds, what's happening at A? And you're reading the diploma and you see that at A, everything is freaking out. It's pressure. Automatically, it's pressure. You know it's pressure. Everything is going up. Then you know, oh, if everything's going up, volume has gone down. So it's a clue visually something's happening. Now, the system does shift to the right, so we have to finish what's happening after this. Shifting to the right means we're making more SO3, so it might go up a little bit more, and these ones will go